Okay, so quickly, just to acknowledge that this work that I'm going to present was done as part of something called the Open Safely Collaborative, involving a huge number of other people, but I particularly want to mention Will and Jonathan, who were involved in the analyses I'm going to present, and indeed the patients. So all the stuff I'm going to present involves data from patients that was collected as part of their care. So a bit of a structure of the talk. I'm going to outline some of the challenges in addressing these sorts of questions in routinely collected health data. Then I'm going to talk about some cohort approaches that you might take. Then I'm going to briefly talk about an alternative approach called the test negative design before comparing the two designs. Does this work?
No.
Okay, I'll leave it.
Something's missing.
Okay. All right, so as we all know, COVID-19 vaccines were developed and rigorously evaluated in randomized trial incredibly quickly after COVID first emerged. So why do we need observational studies? Well, early on, randomized trials either were unable to or didn't address key questions that policymakers were interested in. New variants came along and trials weren't swift enough to re-look at the effectiveness for the new variants. The follow-up of trials tended to be too short to look at things like waning effectiveness, and they also didn't explore things like the benefits of boosters. So for these questions, early on in the pandemic, we were left to rely on observational evidence. So we're going to use routine data, and the studies I'm going to show you are all in the UK, so we need to know something about what actually happened in practice in the UK, because this is where those data came from. So the UK's COVID-19 vaccination programme began in December 2020, and it blows my mind that the WHO declared a pandemic in March, and by December we've got a rollout of a public vaccination programme. It was done in phases of priority, targeting those deemed at highest risk. So the initial priority was people who were aged 80 and above, and those working in healthcare and in care homes. The next level of priority was people aged 70 to 79, and those deemed to have extreme clinical vulnerability. And that was defined on the basis of a number of clinical conditions. So all these vaccines were administered free of charge, and the first two to be used in the UK were the Pfizer vaccine, which was first rolled out on the 8th of December 2020, and then shortly followed by the AstraZeneca vaccine on the 4th of January of 2021. Now, all the trials and the marketing approval were based on an interval between 2 doses of 3 weeks. However, in the UK, that was very quickly decided to expand it to an interval of 12 weeks on the basis that we could get first doses to more people more quickly that way. So that's quite relevant for the studies we're going to look at. So just to give you a picture of what happened, this is the study period I'm going to look at. On the left hand of the graph is the 8th of December, when the Pfizer vaccine was rolled out in the UK, and that runs through till April of the following year. So the y-axis is up to 10,000, and this is the vaccine status per 10,000 people. So once the coloured bits hit the top, it means everyone in this group of over 70s has been vaccinated. So you can see initially no one was vaccinated, and there's a very rapid uptake. And about mid-February, almost everyone has been vaccinated, either with the Pfizer in the pink or the AstraZeneca in the blue. And you can see that initially we had some people with the Pfizer being very quickly vaccinated with second dose, but by the time the AstraZeneca came along, only the 12-week period between doses was in operation. So we're going to use linked primary healthcare data. So I'm going to tell you a very little bit about primary care health in the UK. So in the UK, primary care is delivered through NHS primary care general practitioners. So you go see your GP, and that's your first point of contact with the health system. Every time you see your GP, all the information that's collected is stored electronically. And also when you register at a new GP, there's some information that's stored. Now, this information is stored and managed and collected, held by a number of EHR vendors, so private companies who provide the software that do this data software. There's not many of them, and in fact, 2 companies called TPP and EMIS hold most of the market share of electronic health record software in the UK. And the result is that we have several very large research databases built of primary care records that are founded around one or both of these vendors. So the data I'm going to talk about is built around the data held by TPP. So there's lots of primary care research databases in the UK. They're available in a pseudonymized format, and they contain some basic demographics, things like age, sex, deprivation, ethnicity. They contain all prescriptions and diagnoses that are made in primary care, clinical observations like BMI, pulse, that sort of thing, and all referrals. They also tend to be linked to other data sets. So in particular, the data I'm going to look at include death registry data, hospital data, vaccination, COVID testing data. And the data I'm going to use is from something called the Open Safely platform, which is a large research database that was developed in response to the COVID pandemic. Okay, so initially we're going to think about using a cohort approach to address vaccine effectiveness using these types of data. And I'm going to talk through a number of challenges that immediately strike you. The first and foremost is something that we've been talking about all day, so you're very familiar with, which is that we have non-randomized assignment. So we've got the issue of confounding. We also need to think about whether we can capture outcomes appropriately. We need to think about time zero. So when does someone enter my study? Now, it might be obvious for a vaccinated person. They get vaccinated, that's their day zero. But if you're not vaccinated, when does your day zero happen? When should you come in my study? We've got the issue of unvaccinated people rapidly becoming vaccinated, as you saw in that graph. The last 2 are in brackets because I'm not going to talk about them today, but you can handle these issues in very similar ways to what I am talking about, which is the changing variants over time and dealing with subsequent doses. All right, so first problem, and the biggest. So if we've got a randomized study, the randomization ensures that on average, the people allocated to the control and the active arm are similar. And that leads to this beautiful simplicity. We can just compare outcomes between the 2 trial arms and be assured that that is a reflection of the effect of the intervention. In observational data, that doesn't come close to being the case. The people who choose to be vaccinated and the time at which they choose to be vaccinated is very different from those who do not get vaccinated. So we can immediately think of a number of confounders that are going to be relevant. There are demographic factors that will affect whether or not you get vaccinated, and also your risk of exposure to COVID and your susceptibility to COVID. There's clinical confounders, so comorbidities that again make you more susceptible to infection and severe outcomes. There's a number of behavioral traits, so things that influence vaccine accessibility, acceptability, and hesitancy. Region, geographical region, and calendar period. Do you think we have data on all of these in routine data? Some of them, yes, some of them, no. So demographic, clinical, yes. Region, yes, a crude measure. Behavioral things, we've got really very little indication of those sorts of things. So already we're a bit worried about unmeasured confounding. There's a well-known phenomenon called the healthy vaccinee effect, which is it's unusual to vaccinate people while they're very sick. So if you just compare vaccinated with unvaccinated, you're typically comparing a much more healthy population with a less healthy population in ways which are not likely to be captured. In particular, people who are likely to die soon are unlikely to receive vaccinations. And it's weirdly hard to identify people who are very frail from routinely collected data. So again, we're concerned about unmeasured confounding. recent positive test for COVID, again, that's you're less likely to receive a vaccine shortly after having a recent positive test. And obviously that also influences your risk of the outcome. So we've got a lot of confounders, most of which we think we can capture to an extent, some we don't think we can capture at all. This is just about confounding by calendar period. So over the study period I'm going to talk about, this is a graph of the incidence of COVID, and you can see that it hugely varies through the study period. And you can see after the lockdown it did drop rapidly. But obviously if we're going to compare two people at different points in time, their risk of COVID is going to be vastly different. So we need to think quite carefully about how we account for time. In terms of the outcomes, what do we have in routine data? Well, we've got positive tests. Now, in the UK, there was free testing. So you could send off and get a pack of tests delivered to your house. You could do your own test, but then you had to choose to report the result. So the results that we have in these data are from people choosing to get the test in the first place, and then choosing to take the test when they feel symptomatic, and then choosing to go online and tell the relevant authority that they've got a positive test. And people that did all of those steps for the tests are quite different from people who just skipped a few of the steps. I mean, it's dreadful to admit, but I know I did a few tests that I did not log, so I'm part of the problem. So COVID-19 death is a key outcome. We'd really like to be able to study it, but there's obvious difficulties, both for the certifying clinician deciding what is a COVID death, and also for the analyst using what's captured on the death certificate to classify deaths into COVID and non-COVID. There's also a slightly difficult deterministic relationship between a COVID-19 test and a COVID-19 death, where very few people get reported to have a COVID-19 death without a positive test. So that makes it a bit more difficult when you're looking at all those outcomes at the same time. COVID hospitalization, again, there's difficulties deciding whether someone had COVID on admission versus got infected while they were in hospital due to the way that the English data is collected. All-cause death is the objective measure that we have. The problem is, of course, that there's a lot of deaths that are not COVID. So your sort of signal to noise ratio is likely to be the wrong way around. So you might find that any effect on COVID deaths is swamped by the larger proportion of non-COVID deaths. So the picture is not brilliant in terms of the outcomes that we can use. All right, so changing vaccination status over time, another very tricky issue. So my unvaccinated group are going to tend to subsequently become vaccinated. Now, Con had a discussion about the observation version of intention to treat, and he pointed out that there's no such thing in observational data because we have no idea what the intention was. However, there is something that people call intention to treat in observational data, where we just look at what was assigned at baseline, like did this person get prescribed this drug or that drug, and then we say, okay, we're going to assume that the intention is to carry on with that, and we're going to ignore any changes. So we could do this here. We could split people into vaccinated, unvaccinated, and just ignore anything that happens. However, that's going to give us a massively diluted estimate because the unvaccinated will subsequently largely become vaccinated, and then we're comparing essentially two groups that are just the same. So we can't do that. Instead, we're going to censor the unvaccinated when they become vaccinated. So we're trying to target some sort of per protocol effect now. However, by doing that, we're creating something called time-varying confounding. So we're creating a really difficult analytic situation. So if we think about respiratory systems, respiratory symptoms, they're things that change over time. They affect your chance of being vaccinated, and they affect the outcome. So they're creating this thing called time-varying confounding, which we can't account for using things we've been looking at in this course. We need much more complex methods, often called G methods, one of which is inverse probability of censoring. So this we can deal with, but it's complex. The other issue is those who are persistently unvaccinated. So there still remains a very small proportion of people who have never got vaccinated. And they're a small and very select group. And there are concerns about them being very non-comparable to other people in terms of things that we don't have measured. So then again, we've got concerns around unmeasured confounding here. There are certain people who we believe are different for reasons that we simply haven't captured within these data. Okay, so now I've just listed an enormous amount of very complex difficulties, so now I'm going to solve them all with 2 cohort designs. So first, I'm going to talk a bit about the target trial emulation framework. Have you encountered this in the first week?
I was criticising it today.
Excellent. Good, right? So did you talk in detail about what it was? Right, fine. Okay, so the general idea is that for many observational studies, if we have a causal question in mind, it might be possible to think about a hypothetical trial, which is our target trial, which in some senses we're trying to emulate in our data. So we're trying to get as close as possible to this pretend trial. Why would we do that? Well, one of the advantages that's often discussed is that it forces you to be very explicit about who's your population, what's your eligibility and exclusion criteria, what is the intervention or exposure, what's your outcome, what's the time frame. So it makes you be very explicit, which is always a benefit. However, you could do that without thinking about a target trial. It's proven quite useful for identifying certain biases. So in particular, immortal time bias is something that does crop up in a lot of studies using these sorts of data. And thinking about things in this way can help you avoid that particular sort of bias more easily. It does create a sort of checklist of steps, which has its pros and cons. So it does make you think through all the key aspects you need to be considering. So that can be good. And in particular, someone called Miguel Hernan over in Harvard has been very much pushing the concept of target trials and how we should always think in this way if we're thinking about causality. There are some disadvantages. I mean, checklists, they might be good at making you think through the things on the checklist, but they're also very good at making you switch your brain off. So if someone else is doing the thinking for you, you don't necessarily think for yourself. So they're not always a way of increasing quality of studies. If you think back to Monica's lecture on Monday, you'll remember there's lots of questions, lots of studies she showed you where the question can't easily be framed in this way. So there's lots of causal questions that can't be easily embedded or thought of as a hypothetical trial. And there's a risk. When you start saying, oh, this is an amazing way of doing things, there's a risk that you start thinking about other approaches as being less rigorous. And Neil, in particular, has been talking about other studies where a well-designed case control study gives you a much more valid answer than the equivalent cohort study. So if we start thinking about target trials as being the way of doing causal inference, there's a risk that we devalue studies that are actually better at addressing the causal question you're thinking about. So I've put some references there that you can explore if you want. Having said that, in this case, this is a situation where you can quite easily think of a target trial or a pretend trial. So in my made-up trial, my eligible people are adults who are in England and alive on the 8th of December 2020. That's going to be the start of my study period. I'm only going to include people who are 70 years and above, who are unvaccinated at that point in time, and who have no evidence of prior infection with COVID. My 2 interventions, so I'm going to be thinking about a 3-arm trial. My 2 interventions are going to be a first dose of the Pfizer vaccine and a first dose of the AstraZeneca. And the control arm is going to be no vaccination. And in my pretend trial, I'm just going to randomly allocate patients with equal probability between those 3 arms. And my outcomes I would like to study are positive test, COVID hospitalization, COVID death, and all-cause death. And I'm going to follow everyone up until the 12th of April, which is about 4 months trial period. So this is what the data looks like in a very stylized form. So each of these lines represents a person. So here we've just got 6 people. The triangles represent vaccination. The circles represent the event. So let's imagine that's COVID-19 death. And the rectangles at the end indicate my end of study. So people come into my study on the 8th of December, and they're followed up. And some of them will receive vaccination and then carry on being followed up until either they have the event or the end of study. Okay, so how am I going to make a trial out of this? Well, I'm just going to start at day 1, and I'm going to create a pretend trial out of people in my database on day 1. I'm going to look at who got vaccinated on that day and say, you're going to be my vaccinated arm, and the people who did not get vaccinated on that day are going to be my unvaccinated arm. And I'm going to follow them up from them. Now, vaccinated people, I follow up until they get the event or end of study. Unvaccinated people, that's the purple, I'm going to follow up until they get vaccinated or have the event or end of study. Now, it's not really a trial, that's pretend, so I've got to assess confounders. So just before they go into my pretend trial, I'm going to use the data set to look at things like their age, sex, ethnicity, and so on and so forth. So I could just stop there. I could say, this is my trial. I'm just going to analyze it. Why is that a bad idea? What information on this graph am I not using? Yeah, all the grey lines. So the grey is the time that's not being used. So in particular, people who start off unvaccinated, become vaccinated, there's a lot of follow-up time that we could be using that we're not using. So how are we going to make the best use of that data? Well, we're just going to do another trial. We're going to put trial 1 to one side, keep that data, and we're going to start another trial, trial 2. Now, I'm going to reassess people for eligibility. And remember, one of the things that you have to be eligible is you have to be unvaccinated. So the first and the fourth people who've already been vaccinated are no longer eligible to be in a trial. So they're just gone. So then I look at who got vaccinated on this day and who didn't. And that separates people into my treatment arm and my control arm. So in this case, my treatment arm is just that one person, number 2, who I'm going to follow up until the event or end of study. And then the untreated people, the unvaccinated, I'm going to follow up until end of study, event, or until they become vaccinated. And I need to assess confounders again, but I'm not going to go right back to the beginning of the study period. I'm going to assess confounders just as they go into this new trial. So you can see that the period at which I assess confounders has shifted, and that's quite important. So I just keep doing that right till the end of my study period. So I'm going to end up with 120 different trials. So it's going to use a lot of the data. So let's look at the target trial and what we've done. So in terms of eligibility, I've more or less implemented the eligibility criteria that I wanted, although I've added the criteria that they have to be in my database. So they have to be in one of the relevant practices. Intervention is the same, control is the same. Treatment assignment is the one that's hugely different, obviously. In my pretend trial, everyone's randomized, it's all beautiful. In this case, it's not. So people choose whether to be vaccinated. So I'm going to replace that random allocation with the massive assumption that we always make in observational studies, or often make, no unmeasured confounding. So I'm going to assume that I've measured all the relevant confounders, and I'm going to control for those relevant confounders. And the way I'm going to do that is just use stuff that we've done today. I'm going to do some sort of regression adjustment within each trial, adjusting for all those confounders I measured at that trial's baseline. In terms of the outcome, What we did was we used all of those outcomes, but we didn't use COVID-19 deaths because of these concerns around the connection with the test. And in terms of follow-up, it's exactly the same. Right. Now there's one, oh, sorry. Yeah.
I just wanted to now detect that people will only develop antibodies and an effective response several weeks after vaccination.
Well, so this is one of the things about viewing it as a trial. So if you were just going down a standard observational study approach, you might say we're not going to start follow-up until 2 weeks after vaccination. But Miguel Hernan is very strongly in favour of not doing that. He said if you got a trial, you wouldn't do that because you've balanced things at baseline. So you'd include follow-up time right from baseline, and therefore that's what you should be doing here. No, because if you managed to successfully control confounding, you'd have equal numbers of events in both arms. Yeah, so that's a very good point, thank you. So we did an additional thing, which was we added in a component of matching. You don't need to do this, but in our case, we had a database of about 3.5 million people, and we're taking out this trial on every day for about 120 days. So you can imagine if we included everyone who's eligible for each trial, we could end up with 120 trials, each containing a few million people. You've got a lot of data. So instead, on each trial, we took every vaccinated person and matched them one-to-one with just one unvaccinated person. And if you cast your minds back to when I was talking about the difficulties about censoring the unvaccinated person when they got vaccinated, when you match, there's actually a really simple analytic solution. So we don't need to do all these fancy methods in the case of matching. We can just censor both people in the matched pair at the same time. So in the first matched pair, the unvaccinated person gets vaccinated shortly thereafter, and to deal with that, we're going to censor both the vaccinated and the unvaccinated person at the same time. And it turns out that handles this very complex time-varying confounding situation very simply. So that's a great bonus. So we're just going to do that throughout our trials. Okay, so let's briefly revisit the challenges and think about what we've done. So for non-randomized assignment, we have matched the vaccinated to the unvaccinated. Within each of these pretend trials, we're going to adjust for all the baseline confounders that we've measured. And we've imposed the eligibility criteria at the start of each trial period. And by doing that, we've removed the time-varying confounding that would otherwise exist. In terms of outcomes, we're ditching COVID-19 death. We're using everything else, but just accepting that there's potentially low sensitivity and maybe some differential misclassification that we might need to worry about later. In terms of time zero, this trial approach gives us a very simple solution. So your day zero is just the day that you enter your trial. The unvaccinated people becoming vaccinated, we're going to censor them when they become vaccinated and also censor their match. In terms of the pool of unvaccinated becoming small, the matching naturally just stops creating new trials once there's not enough people to provide matches. So again, it's a sort of natural way of dealing with the problem. Right, I'm just going to very briefly mention a different, yeah, sorry. So, yeah, so you censor no matter what the reason for leaving is. Yeah, so the matched pair always stops follow-up at the same time together. Now, before sequential trials became a thing, this is the way you would have done it. So we would have just done the one trial, as I said earlier, but instead of throwing away the data after an unvaccinated person becomes vaccinated, you would have kept it in and just thought about vaccination status as a time-varying characteristic. So that's perfectly possible. The problem here is that now vaccination receipt is subject to time-varying confounding. So the analysis to get an appropriate answer from this is incredibly complex compared to what I've been discussing. So for a start, if you want to think about what you're emulating here, what trial might give you the same answer, it's a really weird trial. So it's a trial where you determine eligibility at the start, but don't immediately randomize people. You kind of wait, and every day you do a bit of randomization. You take people who haven't yet been randomized, and you randomize some of them to receive treatment. So it's a funny trial to think about. You've got time-varying confounding, so you need to use something like marginal structural models, which is very complex. It's much harder to estimate absolute risks, which is a problem. And you have positivity violations, because people who had a positive test during follow-up, I didn't allow them to be in subsequent trials. So that was easily handled in the previous approach. But in this approach, we've just got a problem, and there's no good solution to it. So I'm not going to consider this approach further, basically. Right, so let's have a look at what happened when we did this. So in this huge research database, we had 3.3 million people who were over 70 and who were alive at the start of my study period. We removed people if their vaccination data were unreliable, if they had only recently joined their general practice, so we weren't confident that we knew enough about their comorbidities and their health status. We removed health and social care workers and care home residents because they had likely been vaccinated already through a different route, which wasn't necessarily in our data. We tried to remove people who were on end-of-life care because they were very unlikely to be vaccinated. And then we made some exclusions for missing data, and we excluded anyone with evidence of prior infection. So that gave us 2.7 million people in what I'm going to call the base cohort. So that's the data from which I'm going to extract my fake trials. So out of these, people ended up in 3 groups. Either they never got vaccinated, they got vaccinated with the Pfizer vaccination, or they got vaccinated with AstraZeneca. Of the middle group who got vaccinated with Pfizer, we managed to find a match for 88.5% of them. So we managed to match most. Of the AstraZeneca people on the right, we managed to find a match for almost all, so 99.7% of them. And there was just over 1 million of each of those. So who were they matched to? Well, they were matched on age within a couple of years, sex, region, and an index of clinical vulnerability. The controls were drawn from all 3 groups. So someone who got a Pfizer vaccination could have been matched to someone who never got vaccinated, someone who subsequently got a Pfizer vaccine, or someone who subsequently got an AstraZeneca vaccine. So the matches are drawn from across these 3 groups. Hopefully that's clear. Okay, so let's have a look at some of the baseline data. So we've got 2 matched groups now. Over all of the trials, 1.2 or so million people got the Pfizer vaccine and received a match in their trial. So for this table, we've just shoved them all in one data set to describe them. So the first 2 columns show the matched pairs for the Pfizer trials altogether for the vaccinated and unvaccinated. The 2 right-hand columns show the matched pairs for the AstraZeneca vaccinated and unvaccinated. Now the top line shows a summary of age. We matched 1-to-1 on age, but not exactly, within a few years. So you can see that if we compare the vaccinated and unvaccinated for Pfizer, we've got very, very similar age distributions. Not identical, but very similar. On the right-hand side, for AstraZeneca, same picture. They're not identical, but very similar. The second row is sex, where we matched exactly. And you can see that within the Pfizer comparison and the AstraZeneca comparison, we have exactly the same numbers as you'd expect. We didn't match on BMI, but we did match on this clinical vulnerability. So we might expect it to be similar, but not the same. And that's exactly what we see. We didn't do any sort of matching related to vaccine hesitancy. And so perhaps, as might be expected, those in the unvaccinated group had a lower proportion of previous vaccination for flu. So that was the best we could find to capture the concept of vaccine hesitancy. In terms of outcomes, over that whole base cohort that I'm extracting my trials from, we had about 500,000 person-years of follow-up, about 38,000 positive tests, and around 20,000 COVID deaths, hospitalizations, and around 20,000 deaths. And the graphics on the right just show how that split is between the vaccinated and unvaccinated time. And you can see from the top left graph, most of the time was unvaccinated. But if we compare that to the top right graph, even more of the positive tests were in unvaccinated time. So we're seeing more of the outcomes in the unvaccinated time than perhaps we would expect compared to the follow-up time. So already a bit of an inkling that we're seeing more events in the unvaccinated. And this is just a quick graphic to show about the matching. So the dark colours are those that received a match for AstraZeneca on the left, Pfizer on the right. And the lighter colours at the top are people who we couldn't find a match for. And you can see as we go through the study period, at some point we start to struggle to find matches. So that's sort of naturally dealing with the fact that there are fewer unvaccinated people. So we accounted for a number of demographic confounders, a whole bunch of comorbidities, and flu vaccination as a measure of vaccine hesitancy. So we're going to analyse each of these trials separately, and then at the end we're going to meta-analyse the results, so take an average. And you're going to have a lecture about that on Thursday, I believe. We're going to fit a Cox proportional hazards model, which we'll learn about on Friday. We're going to adjust for all our baseline confounders, and we're going to look at the effect of vaccination over and allow it to change over time since when you got vaccinated. Okay, so for hospitalisation, this is what we got. So 1, the flat line at 1 represents no effect. Anything below that represents the vaccine being effective in preventing hospitalisations. Now, I want to draw your attention to this part. So this is the first 2 weeks after vaccination. And this relates to the question I got asked earlier. Do we believe this? If you get vaccinated against COVID today, are you going to have 80% protection by tomorrow? No. I mean, we simply, biologically, we do not believe these results. And even after that, we might expect something more like that than the lower estimates we're seeing. So we're seeing a massively exaggerated effect of vaccination compared to what we would expect based on comparison to other studies of various designs. So slightly disappointingly, this looks like there's unmeasured confounding that we simply haven't captured. Same sort of picture when we look at COVID tests. Same sort of picture when we look at death. So basically a massive bust. So have I just wasted half an hour of your lives? Slightly. Let me briefly talk about an alternative design that we could use using routine data. So this is the test negative design. Now the basic concept is we're only going to look at people who've had a COVID test. And we're going to split them into 2 groups. We're going to split them into cases, so people whose test was positive, and controls are the people whose test was negative. And we're going to compare the cases and controls in terms of their vaccination status. So what sort of design is this sounding like? It's just a case control study, which we know all about analysing. So we're going to adjust for potential confounders using exactly the methods we've been learning this week. So it's good because it was designed to remove hard-to-measure confounding, particularly in terms of health-seeking behaviour and testing access. So it might take account of those sorts of things like vaccine hesitancy as well as part of that. That's the hope. It's widely used, so there's a long history of use in influenza, and generally in the influenza setting, it's been found to reproduce results from randomized trials quite well. There's been a flurry of publications about should we be using this design in COVID, and there's a lot of criticisms. It doesn't remove confounding, so we still have to worry about unmeasured confounding. And there's a number of other potential biases that we need to think about. So let's have a quick look at an example. So this is a test negative study in England. Very similar design to ours otherwise, so 70 years and above. People who were vaccinated in people who had a test in a fairly similar study period, December 2020 through to February 21. So it's the first part of my study period. These are people who, when they got the test, they said, I'm getting tested because I have symptoms. And they had no evidence of prior infection. The interventions were the same as ours, and the outcomes, they looked at a similar range of things. Similarly, it used routine data, but they didn't have primary care data, so they don't know anything about people's comorbidities, so they weren't able to take account of that sort of confounding. And the analysis was the logistic regression that we know and love by now, adjusting for all confounders. And this is their results. So, just like ours, in the first couple of days after vaccination, we get slightly weird results, suggesting that something fairly odd is going on. But by 2 weeks after vaccination, we get results that are very believable and are consistent with randomized trials. So it looks like this design has done a much better job of accounting for confounding. Okay. So, should we just abandon the whole target trial cohort approach in these sorts of data, or is there still hope? Well, I'm going to leave you with a final example comparing the two designs. And I'm going to move away from effectiveness to comparative effectiveness. So now, instead of trying to say, is the Pfizer vaccine effective versus nothing, I'm going to compare the two vaccination types. So Pfizer versus AstraZeneca. And there's two studies. So the one in the middle is a cohort approach, again using this trial emulation framework. And on the right-hand side, we've got a test negative design. The population was slightly different. So the trial emulation used health and social care workers, whereas the test negative used all adults. Similar vaccination period. The exposures were the same, and they both looked at COVID-19 positive test and hospital admission as outcomes, and both used linked primary care data in the UK. They used slightly different measures. One used difference in cumulative incidence at a particular point in time, and the other used the average rate difference, but they're fairly comparable measures. And the results are at the bottom here. So we've got an estimate and a confidence interval. And we can see for positive test, we've got an estimate of minus 2.04 per 1,000, indicating that if everyone was vaccinated with Pfizer, we would expect to see a lower rate by 2 per 1,000 than if everyone was vaccinated with AstraZeneca. And that's compared to an estimate of 1.6 in the other study design. So we've got incredibly complementary answers here. And similarly, for hospitalization, we've got very similar results. So the main difference here is that one study was bigger than the other, but otherwise we're seeing very, very similar results. So where does this all leave us? The first thing I have to say is it's incredibly complex to address a causal question in these sorts of routine data, largely because of this non-randomized exposure issue and the fact that we do not have data on some key confounders. It's particularly hard when we want to look at the causal effect of an intervention compared to nothing. So we might think about that as trying to emulate a placebo-controlled trial. And that almost never works in observational data, certainly in routinely collected data. And the reason is that decision to treat with something usually is in response to factors we haven't captured. On the other hand, when we look at comparing different treatments, different drugs, different interventions, then that same action has been taken, even if they've chosen to go down different paths. So comparative effectiveness is usually much more successful, and we can usually justify the assumptions much better. And similarly, looking at things like booster comparisons tends to work better because it's a group of people who've all chosen to be vaccinated. We can never rule out unmeasured confounding in any of these designs. What we can do is build in checks that will indicate that we haven't succeeded in removing it. So looking at that vaccine efficacy in the first 14 days post-vaccination is a good way of seeing whether you've been successful. And I mean, okay, we weren't, and that's all bad. But at least we knew that. So you need to build in these sorts of sensitivity analyses that will tell you if you've got a problem. In terms of test negative design, generally in COVID, they've been very successful. They have their own limitations and potential biases, but generally have been relatively robust in the situations I've seen them in. However, in situations where there's no longer routine testing going on, you simply can't use them. So we're back in the situation where all we could do is this sort of cohort type approach. And the final thought is, when you can get similar results from two very different designs, where the different designs require completely different assumptions, it adds huge confidence to the results. So the target trial approach and the test negative approach, when they both gave us the same answer, we can be very confident that it's right, because it's unlikely that both sets of very different assumptions have been violated, but somehow coincidentally given us the same result. And that all harks back to this idea of triangulation, which I think you're going to learn about next week. Okay, that is me done. Thank you.